Okay, section 8.3 is going to show us some more techniques of integration. We're going to be working with trigonometric functions. And let me start with kind of a polite reminder on a couple things. First of all, the basic Pythagorean theorem is something that you should all know. I mean, it's the one theorem that I really expect you to know from trig. And if you know that one theorem, then we can get a lot of other stuff from it. For instance, if I take this and divide everything through by cosine squared of x, then I get something else pretty special. Sine over cosine is which function? Tangent. So tangent squared of x plus 1 equals what? Secant squared. And of course you can move that 1 to the other side, so tangent squared of x equals secant squared of x minus 1. Likewise, you can move around your original identity. Sine squared of 1, or sine squared of x equals 1 minus cosine squared of x, or the other way around. So a couple nice friendly identities that we can get from this one. Got those two there. And it just comes from knowing your basic Pythagorean theorem. Got these two here. So in a heartbeat, 4 identities follow from that basic one here. Now one other reminder here. That is the derivative of the tangent function. What's the derivative of tangent? Secant squared. And the derivative of the secant function? Yeah, secant tangent. All right, so we're going to use these. I assume you know the derivatives of sine and cosine. Our goal in this section is going to be to try and use some of these identities and these derivatives to help us integrate. And part of the way we'll do that some of the times is by trying to split off your du term, which is going to mean something like this or like this in the case of a secant or a tangent function, and sine or cosine in terms of integrating a function that involves sines and cosines. We'll start with problem number 4. The integral of sine cubed of 3x dx. Now the challenge you're going to face is to try and set up your integral so that you can make a u substitution. But to do that, you have to have a du term around someplace. So here's what I'll do. I'm going to manufacture my own du term. And I'll do that by rewriting this as sine squared of 3x times sine of 3x dx. Well, that doesn't help out too much because I don't necessarily have a du term. Derivative of sine is cosine. But I can change things around a little bit. I've got this term here. What's this the derivative of? If that was going to be as my du term, this is the derivative of what kind of a function? You don't have to give me the exact one. Sine is the derivative of cosine. So looking over here, I can say, you know what? That's really 1 minus cosine squared of 3x. Okay. So that helps out a lot. Why? What does that allow me to do now? Yeah, now I can make a u substitution. Now, don't let u equal the whole thing here. Let's just set u equal cosine of 3x. Then du is going to be minus sine of 3x times 3 times dx. But in using the Pythagorean theorem here and splitting off this term, what I did was I split off my du term. So that's my du term. So I've got this and this. Everything else has to go to the other side. So it's going to be a minus 1/3 du equals sine of 3x dx. I think I'm in good shape to make my substitution. That's going to be the integral of 1 minus u squared times negative 1/3 du. The negative 1/3 comes out in front. In fact, I think we can just integrate this right here. It's going to be negative 1/3 times u minus u cubed over 3. And I suppose you can probably get somewhat fancy with this if you want to. You can factor out a u. You can use your Pythagorean theorem more. But let's just kind of keep it simple. U was cosine of 3x minus cosine of 3x cubed. And I'll put that cubed here to cube the whole function over 3 plus a constant. You could clean this up. I'm sure I could get a sine cubed or something like this out of this, but let's leave it like this. The point is not to really get too fancy with our algebra or trigonometry here. I'm pretty comfortable with that. Okay. Maybe I will. One of the things I do is sometimes I'll look at the problems I do in class and I'll put them on the exam. So, but one way or another, they are coming from the book. Let's try problem number 8. So the integral of cosine to the 5th. I'm going to replace their t. They've got a t there. I'm going to use an x. So cosine to the 5th of x over the square root of sine of x dx. Now, one big problem that we have here is that we've got this square root of sine of x in the denominator, which is kind of a pain. So we're going to need to play around with this and try and manufacture a du term. Realistically, I'd like to get rid of that sine of x here somehow with a u substitution. So if u is equal to sine of x, what should be in my du term? Cosine of x. So let me start by splitting off a cosine. So I'll write that as cosine to the 4th of x times cosine of x square root of sine of x dx. Now I've got a good candidate for a du term. The unfortunate part is that this is my du as long as u is equal to sine of x. That still leaves me stuck with this cosine of x term. So how could I rewrite that in terms of sines? Any suggestions? Don't have to go to integration by parts. All right, so, well, it's 1 minus sine if I had a cosine squared, but I got a cosine to the 4th. Ah, good deal. So what we'll do is we'll think of this as cosine squared of x squared again times cosine of x dx over the square root of sine of x. But now I can get rid of the cosine squared with a 1 minus sine squared. So the integral of 1 minus sine squared of x squared times cosine of x dx over the square root of sine of x. All right, so now I'm in good shape because I manufactured my du term right here. That's my du term, and now I can let u equal sine of x. So let's play with that a little bit. So here's my u substitution, u equals sine of x. Du is cosine of x times dx. So then what happens? Well, This becomes the integral of 1 minus u squared squared again over u to the 1/2 power times du. At least it's looking a little bit more hopeful. Andrew, any suggestions? What can we do here? Kind of reminds me of one of the problems we did earlier in section 8.1. How about if I squared that out? I don't want the imperial march here. It's not that bad. All right, go away. Yeah, FOIL it out. Sure, FOIL it out. So it's going to be 1 minus 2u squared plus u to the 4th. Okay, that's looking better. That's looking closer to something we did in 8.1. Can anyone make a suggestion here? Yeah, we can break it up. So, breaking it up, this is, well, it's 1 over u to the 1/2 minus, well, let's subtract exponents, right? So 2u to the 3/2 plus u to the 7/2 all du. And maybe you want to write that as u to the negative 1/2. But this is just integrating polynomial type function. It's not exactly a polynomial, but it's similar. You're going to add 1 to the exponent and divide by that same exponent. So u to the 1/2 divided by 1/2 minus 2u to the 5/2 divided by 5/2 plus u to the 9/2 divided by 9/2 plus your constant. We might want to clean this up here before we start playing around with more stuff. So that's going to be 2u to the 1/2 minus 4/5 u to the 5/2 plus 2/9 u to the 9/2 plus your constant. All of these share a common factor of u to the 1/2. So if I factor that u to the 1/2 out, it's going to make things a lot cleaner. So let me do that. U to the 1/2 times 2 minus 4/5. If I factor out a 1/2, how many u's am I going to be left with? 4/2, which is squared. Or 8/2, which is u to the 4th. So that's about as clean as I want to try and bother and get it. Let's plug back in for u. I'll have the square root of sine of x times 2 minus 4/5 sine squared of x plus 2/9 times sine to the 4th of x plus c. What do you think, Ted? Another test question? Want this one? Yeah? Okay, sure. All right, good deal. 10? All right. Is there anything on problem number 8 you'd like me to review a little bit more? Maybe something I wrote too fast. Doing okay on that one? All right. Yes. Sure. Absolutely. Well, you do your u sub after you've set up your integral to have the du term. And that's what we did back at the start. Is I realized, you know what? I'm going to want to get rid of this sign here. And that means I'm going to use a u substitution. Well, if I'm going to do a u substitution, I know what my du term has to look like. So I played with my integrand in order to get that.
And then you also put that cosine squared to
Yeah.
terms of u as well.
So that I could again get rid of everything except what I needed to, which is I needed to leave myself with just sines and my du term.
So you want to keep it like all sines or all cosines besides the derivative.
Exactly.
Okay.
Yep. And so that was the logic behind splitting this up like we did. Okay. Good questions. Thanks, gentlemen. Now, on your test from last week, one of the problems that we did was finding a centroid. Over the weekend, I happened to see one of my colleagues who was testing his Calc 2 students, and his test, his question for the centroid was much more difficult, and he had to give the students this formula because they hadn't covered it yet. It's called the power reduction formula. Cosine of theta is equal to 1 plus cosine of 2 theta divided by 2. And sine squared of theta equals 1 minus cosine of 2 theta over 2. I'm not sure it's really worth the time to try and show you where these formulas come from. Let's just use them and practice with them. These are going to be useful when you have even powers of sine and cosine. With your odd powers, the first two examples, we're able to split something off because we had an odd power of a sine or cosine. But if you have an even power, it's not so easy. So, let's see. We'll do problem number 12 as an example. Integral of x squared times sine squared of x dx. Now the unfortunate part about this one, like I said, is that, okay, you're stuck with the sine squared. Even if you turn that into 1 minus cosine squared, you're still not going to be able to split off that du term. So your next best friend then is one of the power reduction formulas. So in this case, it's this one right here. And let's plug that in and see if and what good that does us. Well, that would be the integral of x squared times 1 minus cosine of 2x divided by 2 dx. The nice thing now is that at least my trigonometric function is to the first power, and I can integrate that. We can't integrate sine squared directly. We don't have an antiderivative for that off the top of our heads. But here, let me do this. I'm going to factor out the 1/2, and I'm going to distribute the x squared. So it's going to be the integral of, let's see, x squared minus x squared cosine of 2x dx. Okay, I can further split that up as 1/2 the integral of x squared dx minus 1/2 the integral of x squared cosine of 2x dx. Did we make any headway? Did doing this help out? Yeah. The first one we can integrate, right? Our Calc 1 students can integrate that one, but I need to integrate that second one. Nish, any ideas? What would I do there? Yeah, integration by parts. Yeah. In fact, let's be more specific. Integration by parts, but how? What am I going to do to integrate that by parts? Table method, yeah. So let's just kind of do that off to the side and then put all the results together. So it's this part right here I'm going to integrate using the table method. We'll throw the 1/2 in when we're all done. So integral of x squared cosine of 2x dx. U equals x squared, and then 2x, then 2, then 0. dv equals cosine of 2x. And why don't you take a moment to see if you can't run yourself through and find all the successive antiderivatives there. Remember, they're going to have to do some changing of signs and dealing with the constants. See if you can't come up with that. Actually, you know what? I don't need the last one, do I? Never happened. Remember, +1, -1, +1. These are our multiplication factors. Con. What terms am I going to get here for the antiderivatives? Good. Good. Perfect. Thank you. All right. So putting this together with this in our table method, I'm going to get x squared over 2 times sine of 2x. Minus and a minus gives me a plus. The 2's will cancel. So it'll be plus x over 2 cosine of 2x. And then a minus 1/4 sine of 2x plus a constant. We'll take care of that plus a constant when it's all done. I need to multiply this result by 1/2 and include this result. So this is going to be 1/2 times x to the third over 3 minus this mess. So let's see if we can't put it all together. It's going to be x to the third over 6 minus 1/2 of all this. So x squared over 2 sine of 2x plus x over 2 cosine of 2x minus 1/4 sine of 2x plus our constant. Yay. Don't want to forget the constant, so I'll come in another point. So what made this one work is that we were able to get rid of the even power of your cosine, or even power of the sine with the power reduction formulas. So, any thoughts on problem number 12 there?
How did the beginning of it? You went off to the side. How did that?
So this side calculation is what I did right here, and the result of this side calculation was this. So I needed to take the side calculation and times it by the negative 1/2. So here's your negative 1/2 times my side calculation, and then this was the other part that we didn't really need anything fancy for. So that gave me the 1/6 x cubed, which is right here. Yeah, no, appreciate it. Help me assemble that one. Okay. Anything else on problem number 12 here? Let's do a couple that involve some tangent and secant type functions. We'll start with problem number 38. Come on. There we go. Yeah, so take care of that in a second. Stay. Good boy. So in 38, we've got a differential equation, dy equals secant squared of x times tangent squared of x. And this passes through the point 0 and negative 1/4. So when you're all done, we'll solve for y and determine the value of the constant. We've seen this stuff before this evening. We're going to multiply both sides by dx, get dy equals secant squared of x, tangent squared of x, dx. And this one's kind of a friendly break into working with our tangent and secant functions. I'm going to integrate this one on both sides. So here and here. On the left-hand side, of course, I'll get a y. But on the right-hand side, I got to slow down a little bit because I don't know how to directly integrate this thing, but this one's set up pretty nice for you. Can anyone see why? We can use identities, but we really don't even need to go to the identities for this one. Derivative of tangent is what? Secant squared. So we've already got our du term just sitting there for us. This is the low-hanging fruit, all right? We don't need to do anything fancy on this one. Let's just go for the easy thing, and that is a u substitution. So it's suggesting that this is our u substitution because we've already got a du term built in. U equals a tangent of x. Du is secant squared of x dx. Perfect, because that's right here. I get the integral of u squared du. Which of course is u cubed over 3 plus a constant. Substitute back in for u. Y equals 1/3 tangent cubed of x plus a constant. All right, looking pretty good. The only thing left then is to solve for the constant. So this passes through the point 0 and negative 1/4. So plugging those in, x and y, I get negative 1/4 equals 1/3 the tangent of 0 cubed plus c. Unfortunately for us, the tangent of 0 is what? 0. So that disappears altogether, and c equals negative 1/4. Overall, my equation is y equals 1/3 tangent cubed of x minus 1/4. Wow. Hey, by standards,
that was easy.
All right, it wasn't terribly easy, but compared to a lot of our problems tonight, it wasn't. It was kind of easy. But did you see the magic that made this thing work? We had a du term already sitting right in our integrand. derivative of tangent is secant squared. We had a secant squared there, so we're in good shape. Sometimes you're going to have to make that happen. Sometimes you won't. It's just going to depend on the particular problem. So a good one to follow that up with is problem number 26. Are we okay with 38 before I move on to 26? All right. So 15, yes. The integral of, let's see, tangent to the fifth of 2x, secant to the fourth of 2x dx. We're not set up quite as nice in this one as we were in the last one, are we? All right, we can play around with it a little bit.
Break up the tangent.
We could. Yeah, I think I'm liking the idea of breaking up the secant. Let's think here. Tangent to the fifth, 2x. What way would you break up the secant? Well, how about if I did secant squared of 2x times secant squared of 2x dx. Now, what does it look like I'm heading for? What am I leaning towards? All right, u should equal this. What u substitution do you think I'm headed for? U equals tangent. So if u equals tangent, think of the next step. What's the du term? Secant squared. So I need to keep this for my du term. This is going to be part of my u term, so I need to do something with that secant squared term. I'm open to suggestions. Ah, there you go. We're going to start using the identities here. So going way back to the start there, secant squared was equal to tangent squared plus 1. So this is tangent to the fifth of 2x times tangent squared of 2x plus 1 times secant squared of 2x dx. Perfect. This is exactly what I want. Everything's in terms of tangent except for my du term here. This is exactly what I wanted. So now I'm in good shape to make my u substitution. But you see what we did here? We split off our du term. And that's the key in all of these things. You're splitting off that du term in order to find an antiderivative. U equals tangent of 2x. Du is secant squared of 2x times 2 dx. Which is pretty close to what I have in the integrand. So I've got secant squared 2x dx. I need to get rid of the 2. So let's divide that over to the left-hand side. That's 1/2 du equals secant squared of 2x dx. Perfect. Let's see how this thing finishes up. Now notice you could, if you wanted, you could distribute this. I'll distribute it after I do my u substitution. I'm going to get u to the fifth power times u squared plus 1 times 1/2 du. I'll bring the 1/2 out in front and distribute. I'll get u to the 7th plus u to the 5th du. or 1/2 u to the 8th over 8th plus u to the 6 over 6 plus our constant. Overall, 1/2 times 1/8 tangent to the 8th of 2x plus 1/6 tangent to the 6th of 2x plus your constant. And I do have my constant in there, yes. Okay, not too bad. How are we looking on 26? Thumbs up? That constant is important. There's things, and we've seen it when we solve differential equations, you can't do without that constant. For instance, you can't build a houseboat without that constant. So, let's build a houseboat. What we'll do is we're going to integrate the function 1 over cabin d cabin. Now, I trust that you all know your Calc 1 very well. What's the integral of 1 over something like this? It's the log, right? So you've got a log cabin, but the important part was to remember the constant, right? So a log cabin plus the c, there you go. There's your houseboat. Yay! Give it up. Come on. Math jokes. Yay! All right. Aye, aye. At your service. All right. So just a little, very little humor, right? Let's keep going with another one of these. Yeah, let's do 58. I mean, we've done a few hard ones tonight, so let's do something that's not quite so onerous. The integral from 0 to pi over 3 of the tangent squared of x dx. This one works out so nice. It's actually almost funny. I don't know. Usually I'd institute the 9 o'clock rule. That after 9 o'clock, I don't really ask much of you guys because you've been here for 3.5 hours, and I know you're like, oh God, you're looking at your watch, tapping it like, move, come on, we got to be almost done. But on this one, does anyone have any insights? It's not going to be integration by parts. Is there anything we can do on this one? Brilliant. Let's change this to secant squared minus 1. How does that help us out? Well, it helps us out wonderfully because we know the antiderivative for both of these. What do you differentiate to get secant squared? Tangent. What do you differentiate to get 1? X. Wow, isn't that cool? Tangent of x minus x between 0 and pi over 3. At 0, both of these functions disappear, so it's just a matter of, okay, I need the tangent of pi over 3 minus pi over 3. And the tangent of pi over 3, you know, a lot of you might not know that off the top of your head, so let me remind you of a trick that I may or may not have shown you earlier. If your calculator's in radian mode, let's do tangent of pi divided by 3. And it might not be a familiar number. You might look at it and go, God, I don't know. So here, try this. Let's hit the square button. So if I square it and I get 3, what did it start out as? Square root of 3. Yay! Square root of 3 minus pi over 3. Yay, I think this deserves some more love.
That was easy.
Yeah, cool. All right. I wish I could tell you they were all that easy. They're not. Some of these are going to be more of a challenge. Um, let's take a look at problem number, I think it's 62. The integral from pi over 6. You know what? Tell you what. We're not even going to do the limits integration. I don't want to get bogged down in that stuff. This is now officially problem 62-ish. We're just going to do it as an indefinite integral. Sine of 6x cosine of 4x dx. Now, in a problem like this, I would give you some substitutions that are on page 529. I don't expect you. I don't even have memorized the product to sum formulas and sum to product formulas. Actually, you know what? I think I am supposed to make you memorize them. So just to make sure that we got that on the video here. But do you understand what I mean here? To you. All right, are we good on that? You have to have them memorized. All right, this is cool. All right, so good. Glad we're around that. So let's take a look at which one of these we need. We need a sine times a cosine. So there's three different forms here. Sine times a cosine. It's this one that we want. So let me copy that down here for us. Sine of mx times cosine of nx equals 1/2 times sine of m minus n times x plus the sine of m plus n times x. Oops, sorry about that. I didn't realize I was pointing in the wrong direction. So the nice thing about this formula is that it turns a product into a sum, and it turns something that would be a pain to integrate into something that we can integrate without much difficulty. The thing to keep in mind is that this is your m and this is your n. So let's see if we can't plug this in. That's going to be the integral of 1/2 sine of m minus n. So 6 minus 4 is 2x plus the sine of m plus n. 6 plus 4 is 10. So 10x. That's kind of nice to be able to do that because now we don't need anything fancy at all to integrate that. That's just going to be 1/2. Now when I integrate sine, I'm going to get a cosine. So I'll get a cosine of 2x. But what constant is going to come out in front? What I picked on in a while? Andrew up front. What constant is going to come out in front when you integrate this term? I've already got the 1/2 here, but when I integrate this, some help? Yeah, negative 1/2. Good. Negative 1/2 minus 1/10 cosine of 10x plus your constant. And you can distribute it and maybe clean up or factor something out. That's fine. But this is where I want to leave problem 62-ish. So. Okay, we comfortable with that? All right. So I typically scan in the notes from each class and post them online. I think I'm up to date. This is going to be a whopper of a file. I don't know about you guys, but I'm at 16 pages by now. So, so couple more here to finish things up. Let's take a look at problem 24. So the integral of tangent cubed of pi x over 2 times secant squared of pi x over 2 dx. I'm going to let you chew on this one for a minute, see what you can come up with, try and figure out what would be the appropriate u substitution. Okay, so I think a lot of you are doing all right on this one. So let's go through it. We'll let u equal, since you've got a secant squared here, and secant squared is a derivative of tangent. So, I mean, it's just begging you for a u substitution right here. We'll let u equal a tangent of pi x over 2. du, you got to be a little bit careful. It's secant squared, derivative of the outside, pi x over 2 times the derivative of the inside. The derivative of the inside is going to be pi over 2 times dx. So the pi over 2 is not part of this, but everything else is. So let me move this to the other side by dividing by pi over 2, or better yet, multiplying by its reciprocal. I get 2 over pi du equals secant squared of pi x over 2 dx. And that's perfect because this and this match. So I've got my du term, and this integral turns into the integral of u cubed times 2 over pi du. So that's going to be 1/4 times 2 over pi times u to the 4th plus a constant. That's going to give me some cancellation. I'll end up with 1 over 2 pi times a tangent to the 4th of pi x over 2 plus our constant. How many people got that one? Yay, good deal. For homework, 1 through 11, 19 through 37, 41, 43 through, let's see, 41, 43, 57 through 63, and 73. That was section 8.3.